Hello everyone, my name is Mariam. This video is for the Independent Learning Center at SQU and it's about Introduction to Probability and Statistics. In this video, I will talk about the counting principles like permutations, combinations, and the general counting rule. And then I will move to the probabilities. And finally, I will talk about the Bayes formula. Starting with the basic counting principle, the rule says that the total number of different ways a sequence can occur is n1 times n2 up to nk. It means that if we have different events, say event 1, event 2 up to event k, each event has its own outcome or the number of outcomes. So to find the total number of outcomes, we will multiply the number of outcomes for each of the events to get the total number. To make things easier, I will use this example. Suppose someone wants to drive from A to B and then from B to C and then from C to D as we show here in the map. Okay, and we already know that to move from A to B we have 2 routes, and from B to C we have 4 routes. To move from C to city D we have 5 different routes. So what's the total number of different routes? So it's going to be multiplication of each of these 2 routes. In terms of the principle, we can assume that the first event, E1, is moving from A to B, while E2 is moving from B to C, while E3 is moving from C to D. So we have 2 outcomes here, we have 4 outcomes here, while we have 5 outcomes here. Then we'll multiply 2 by 4 by 5 to get the final number of possible routes, which is equal to 40. Moving to the permutations, it's an ordered selection of R objects without repetition from total of N objects. So we have total number of objects is equal to N, and we need to select R objects. Then we call this permutations if order is important and repetition is not allowed. And it is denoted by NPR. We can get this either by the calculator, simply NPR, or we can use the formula, which is n factorial divided by n minus r factorial, and we will see this in the next example. Suppose we have a club with 20 members. The offices of president, vice president, secretariat, and treasurer are to be filled. No member may serve in more than one office. How many different slates of candidates are possible? So you see here we have n is equal to 20, the total number of members. We have only 4 positions. These are the positions: president, vice president, secretariat, and treasurer. So you see we have order is important, and we have one important sentence, which is no member may serve in more than one office, means that repetition is not allowed. So you will go directly to the permutations and you will apply the formula or by using the calculator. So you will say 20 PR, it means selecting 4 members out of 20 to get the permutations, and it's equal 116,280. Or you can use the formula as I said. 20 PR means 20 factorial divided by 20 minus 4 factorial, and you can get exactly the same result. Moving to the last way of counting, which is the combinations. It's one way to find the total number of outcomes. A combination of n objects taken R at a time is denoted by NCR. So you see that combination is very similar to the permutation, but the only difference here is that we don't have an order. We don't care about the order in the combination case. To compare things, I will compare the combinations and permutations in one example. So list all combinations and all permutations of the 4 letters when they are taken 3 at a time. So suppose we have these 4 letters A, B, C, and D, and we want to select only 3 at a time. We need to find the selections for the combinations and for the permutations. In the first case, the combinations is going to be 4, C, 3, or 3 objects, letters selected from total of 4. The answer is going to be 4. While for the permutations, 4P3, the answer is going to be 24. 3 objects or letters, selected from total of 4 is going to be 24. You see the big difference between the 4 and 24. Why is that? So the selection is different here. For the first case, for the combination, if we assume I will select first A, B, and C, then I will say, for example, B, A, and C. This is exactly the same. So for the combination case, A, B, C is exactly same as B, A, C because order is not important. While in the permutation case, A, B, C is not same as B, A, C or is not same as C, B, A, and so on. So that's why we have this difference between the combinations and the permutations. Moving to another question. An artist has created 20 original paintings and she will accept some of them in 3 galleries. 4 paintings will be sent to Gallery A, 4 to Gallery B, and 3 to Gallery C. In how many ways can this be done? So we can solve such a question in different ways. Let's see the first way. First, we need to find out what is our n value and what is r. N is going to be the total number of paintings, which is equal to 20. While r here, we don't have only one r, we have 3 different r's. First r, r1 is the 4 paintings that will be sent to A, while r2, 4 paintings sent to B, while r3 is 3 to C, okay? So we can solve this by using the formula. So n factorial divided by r1 factorial, r2 factorial, r3 factorial times n minus total of r, which is equal to 11 in this case, and the final result is equal to 9 here. So it's going to be 20 factorial divided by 4 factorial for A, 4 factorial for paintings to B, and 3 factorials for paintings to C, times n, which is 20, minus the 11 paintings, which is equal to 9, and the final result is given here. Or you can solve it in any other way, like which is shown here in method 2 or method 3. Moving to the sample space and events. Sample space S is the set of all possible outcomes. The number of sample points is denoted by number of S. So S is the represent all set of possible outcomes, while number of S means the sample points or the number. We will take the easiest example. Suppose 2 different coins are tossed and the results are head and tail or tail. For each coin is observed, determine a sample space. So it's going to be the sample space. If we toss 2 coins, then it's going to be either head head or head tail or tail head, or finally it's tail tail. So the number of sample points is going to be equal to 4. They are only 4, and this is our set of outcomes. Another question. A bag contains 4 jelly beans, 1 red, 1 pink, 1 black, and 1 white. Question number A. A jelly bean is withdrawn at random, its color is noted, and it's put back in the bag. Then a jelly bean is again randomly withdrawn and its color noted. Describe a sample space and determine the number of sample points. First, I will find the number of sample points. Since I will first select or draw only one jelly bean from the bag, okay, then it means I have 4 different possible outcomes. So it's going to be 4 times, again, since I will put the first jelly bean back in the bag and I will I will draw another one, then it means still I have 4 different outcomes. So the total number of sample points is going to be simply 4 times 4, which is equal to 16 sample points, and we can list all of them. Here we have only subset of the whole sample space. So the sample space could be like getting first red and then pink, or red and then white, red and then black, and finally red and again red, another red. You can also list the rest of the outcomes. In part B, determine the number of sample points in the sample space if 2 jelly beans are selected in session without replacement and the colors are noted. So here we don't have replacement. It means I will select one jelly bean, I will keep it aside, and I will select another one. So what's going to be the sample points? At the beginning, I will have 4 different outcomes. Okay, I can get either red or pink or black or white. Okay, and then the remaining will be only 3 jelly beans in the bag. So from the 3 I can get any one of them. So the total number of sample points this time is going to be 4 times 3, which is equal to 12. Why is this difference? Again, because we have no replacement. Another question is about rolling 2 dice. A pair of dice is rolled once, and for each die, the number that turns up is observed. Determine the number of sample points. So it's going to be the sample points here. For each die, we have 6 different faces, so it's going to be 6 times 6, which is equal to total 36. A definition of an event. Event E is a subset of the sample space for the experiment. And we have some rules for events. See this example here. Given the usual sample space S, which is equal 1, 2, 3, 4, 5, and 6, for rolling a die, let E, F, and G be the events as following. E is equal 1, 3, 5. It means only the odd values. F equal 3, 4, 5, 6. And G is equal to only 1. Determine each of the following events. In part A, what's the complement of E? E complement means that all the values, or the opposite of E, it means all the values that are not in E. So E complement is going to be the even values 2, 4, 6. Why? Because E itself has the odd values 1, 3, 5. So in part B, we need to find the union of E and F. Union means all the values in E and all the values in F. So E union F means 1, 3, 5. In addition to this, we have also 4 and 6. We have 3, 5 here, but we will not repeat them. We need to find E intersect F, or the intersection of E and F. It's going to be only the common values of E and F. So what are the common values? They are only 3, 5, 3, 5 here. We can also find the intersection of F and G. F has 3, 4, 5, 6. These are the values in F, while G has the value 1. So you notice that we don't have any value in common, means that the result is going to be phi, or an empty set. We can also find the intersection of E and E complement. Since we said that E complement is the opposite of E, so normally we have to find a phi, or the answer is going to be phi or an empty set. Why? Because E is only odd numbers, while E complement is the even numbers. We don't have anything in common, so it's going to be phi. Finally, union. E union E complement is going to be all the values in E and E complement. In other words, it's going to be the whole set. Here is a list of all properties of events. You have to know these properties. Please have a look at them later. Moving to the probabilities, equally probability spaces. S is called an equally probability space if all events are equally likely to occur. This is very important. Probability of the simple event, probability of Si is equal 1 over n. If S is a finite equal probability space, probability of E is going to be the total number of outcomes in E over total number of outcomes in the whole sample space. Okay, so this is the rule of finding the probability of an event E. Suppose we have 2 fair coins and they are tossed. The result is going to be, for the sample space, it's going to be head head, head tail, tail head, or tail tail. Okay, so determine the probability that 2 heads occur, and in part B we need to find the probability that at least 1 head occurs. For the first case, the probability that 2 heads occur, you see the whole sample space here. We have 4 different outcomes, and the probability of getting 2 heads means it's only once out of 4. So probability of event E is going to be number of outcomes in E, which is only 1, divided by total number of outcomes, which is equal to 4. The second probability is about at least 1 head occurs, means that either head head, or head first and then tail, or tail first and then head. So it's going to be 3 out of total 4, as we have here in the answer. Another question, from a production run of 5,000 light bulbs, 2% of which are defective, 1 bulb is selected at random. What's the probability that the bulb is defective? And the second question, what's the probability that it is not defective? The first question is about a bulb to be defective. The answer is given in the question itself. It's only 2% of which are defective, so it's 2%. Or you can answer this in another way. We can say that the total number of light bulbs is equal 5,000, and since we know 2% are defective, so we can find the number of defective bulbs. It's going to be 0.02 times 5,000, which is equal to 100. So to find the probability of defective bulb, it's going to be the number of defective bulbs over the total number of bulbs. So it's 100 over 5,000, which is equal to the same 0.02. The second question is asking you, what's the probability that it is not defective? So if E is probability of getting E is event of having a defective bulb, then E complement is the event of having non-defective bulb. So it's going to be probability of E complement is equal 1 minus probability of E, which is equal 1 minus 0.02, and the result is going to be 0.98. And it makes sense. So P is probability function. We can say that P is a probability function if both of the following points are satisfied. The first one, that the probability of S is going to be between 0 and 1, including 0 and 1, but not greater than 1 and not less than 0. The second point is about the summation of all probabilities in a sample space must be equal to 1. So these 2 points must be satisfied so that we can say it's a probability function. Moving to odds, the odds in favor of event E occurring are the ratio. So we can find probability of E over probability of E complement, and we call this as an odd. Finding probability from odds, sometimes we can use the odds to find probabilities. If the odds that event E occurs are A to B, then probability of E is going to be simply A over A plus B. And we will see this in the next example. We have a student who believes that the probability of getting an A on the next mathematics exam is 0.2. Then what are the odds in favor of this occurring? So if we assume that event E is the event of getting an A grade, then E complement is the event of getting another grade, not A. So the odds is going to be probability of E over probability of E complement. So probability of E is 0.2 divided by probability of E complement is 0.8. So it's equal 1 over 4, or in terms of the odds, it's going to be 1 to 4. Okay, moving to the conditional probability. If E and F are events associated with an equally probability sample space, and you know that the probability of F is not equal to 0, then we have the rule that says the probability of E given F, which is conditional on F, is equal the probability of E and F divided by probability of F. To make things easier, we will use this example. Suppose a bag contains 2 blue jelly beans, say B1 and B2, and 2 white jelly beans, say W1 and W2. If 2 jelly beans are randomly taken from the bag without replacement, find the probability that the second jelly bean taken is white, given that the first one is blue. So the probability that the first is blue and the second is white. So probability that it is white given it was blue. We can apply the formula here. So we will say probability that it is white given it was blue is equal to 2 over 3. How I got these results? Here, the probability of getting the a jelly bean that is blue, or first we can say probability that getting blue and white is going to be 2. Okay, we can get either blue one with white one, or let's say the first one is blue, right? Yeah, so we can get either white one with and white 2 with the blue divided by the total number of blue, yeah, which is equal to 3. Conditional probability, we can apply this formula. It's the same applied here. Okay, one more question. quality control. After the initial production run of a new style of steel disc, a quality control technician found that 40% of the discs had an alignment problem and 10% had both a defective paint job and an alignment problem. If a disc is randomly selected from this run and it has an alignment problem, what's the probability that it also has a defective paint job? So let's find the probabilities first. The probability that a disk has an alignment problem is equal 40%, and the probability that a disk has an alignment problem and a paint job problem is equal 10%. Okay, so we have the probability of A. Let's call the alignment problem as an A, and D is the defective paint job. So probability of A is equal 0.4, while the probability of D and A is equal 0.1. I got all these percentages from the question. So the probability of getting defective problem given it was having an alignment problem, this is equal probability of D and A divided by probability of A, which is equal to 0.1 divided by 0.4, or it is 1 over 4. There is a general multiplication law. It says that the probability of E and F is equal probability of E times probability of F given E, or same as saying probability of F times probability of E given F. We will see this example here that will apply the general multiplication law. A computer hardware company placed an ad for its new modem in a popular computer magazine. The company believes that the ad will be read by 32% of the magazine's readers and that 2% of those who read the ad will buy the modem. Assume that this is true and find the probability that a reader of the magazine will read the ad and buy the modem. So the probability that someone reads the ad is going to be 32%, and the probability that someone read the ad and buy the modem is given that the second one is going to be the probability that he buy or she buy the modem given that he or she read the ad. So we have two probabilities here. We need to find the probability that someone who read and buy the modem. It's going to be the probability of someone read the ad times probability that someone buy the ad given he or she read the ad. Someone buy the modem given that he or she read the ad is going to be the multiplication of the two probabilities to get the final result, which is 0.0064. Okay, let's see one more question. Two cards are drawn without replacement from a standard deck of cards. Find the probability that both cards are red. So what's the probability that both cards are red? We have here no replacement, so I will draw one card, I will keep it aside, and then I will draw another card. So the probability of getting first red card and then another red card is going to be probability that first one is red times the probability that the second one is red given the first was red. So for the first one, the probability of getting first red card is going to be the total number of red cards, which is equal to 26, over total number of cards, which is equal to 52. And then we know that the remaining of red cards is only 25, and the remaining of all the number of cards is going to be only 51. So you will multiply the two probabilities to get the final result, which is 25 over 102. Moving to the independent events, E and F are said to be independent events if either probability of E given F is equal probability of E, or the probability of F given E is equal probability of F. In that case, we call E and F as independent events. Let's see this example. A fair coin is tossed twice. Let E and F be the events: E head on first toss and F head on the second toss. Determine whether or not E and F are independent events. We know that here is our sample space. We have either two heads or head tail, tail head, or finally two tails. Okay, so to find whether these are independent events or not, we can check out the principle here. We can check the two sides of this rule, and if it's satisfied or if they are equal, then we can call them as independent events. So let's first find probability of E. Probability of E is equal to the number of all outcomes in event E divided by the total number of outcomes. We said E is about head on first tooth. So we can get head on first tooth only twice. It's here or here, so it's 2, over total number of sample points, which is 4. So 2 over 4, it's equal 1 over 2. That's it for the first side. Now we can find probability of F given E, okay? So this is equal to probability of F and E over probability of E. This is going to be 1 over 2. We can get only 2 heads, only once, divided by the total number. So 1 over 2. So since the two sides are equal, then we can say that these two events are independent. We have special multiplication law. If E and F are independent events, then we can find the probability of E and F by simply multiplying the probability of E by the probability of F, and that's it. We will take this example. Suppose the probability of the event Bob lives 20 more years, let's say B is 0.8, and the probability of the event Doris lives 20 more years, D, is 0.85. Assume that B and D are independent events. So we have here that the two events are independent. We need to find the probability that both Bob and Doris live 20 more years. So probability of B and D is going to be probability of B times probability of D, which is equal 0.8 times 0.85, and the final result is shown. One more example. 4 cards are randomly drawn with replacement from a deck of 52 cards. Find the probability that the cards chosen in order are King, Queen, Jack, and Heart. Here we have the word with replacement. Okay, so we have replacement means we have independent events. Getting a card with King is independent of getting a card with Queen, and so on. Okay, so to find the probability of getting King, Queen, Jack, and Heart is going to be the multiplication of all these probabilities. So we know that we have only 4 kings, we have only 4 queens, we have only 4 jacks, and we have 13 hearts. And you can find the final result. Moving to the last part of this video, which is about Bayes' formula. The conditional probability of F, given that event E has occurred, is expressed by probability of Fi given E is equal probability of Fi times probability of E given Fi divided by the probability of F1 times probability of E given F1 plus probability of F2 times probability of E given F2, and so on up to probability of Fn times probability of E given Fn. It seems like a complex formula, however it's very easy. You will see this in an example. Suppose microchips are purchased from A, B, and C and are randomly picked for a sampling each camcorder. 20% of the microchips come from A, 35% from B, and the rest from C, which is going to be 45%. Okay, the probabilities that A is defective is 0.03, and the corresponding probabilities for B and C are 0.02 and 0.01 respectively. A camcorder is selected at random from a day's production, and its microchip is found to be defective. Now the question is asking you, find the probability that it was supplied from A, from B, from C, and the final question is about from what supplier was the microchip most likely purchased. First we need to find these probabilities. So we can say at the beginning that we define the following. S1 is for supplier A, S2 for supplier B, S3 for supplier C, to make things easier, and D means defective microchip. So the first question is about, we need to find the probability that it was the microchip was purchased from A. It's going to be the probability that the supplier is A given it is defective, and that was in the question. So the probability of path through S1 and D divided by probability of all paths to D. So the probability that it is S1 given D, by applying the Bayes formula, it's going to be the probability of A, supplier A, 0.2, times the probability that it is defective from A, so 0.03, divided by the same percentage here plus the percentage that it is from B with defective from B plus percentage from C defective of C, and you can find the final result as 12 over 35. This is in case of supplier A. We will move to supplier B, and this denominator is going to be common for all the questions. To answer all of the questions, we will use the same thing here, which is the combination of supplier A with its defective probability, supplier B and defective, supplier C and defective. And the answer is equal to 35. So the probability that it is from B, given it is defective, is going to be the probability of being of the microchip is from B times the probability of defective from B divided by the total answer, which is 35. Here is a mistake. And then probability that it is from supplier C, given it is defective from C, so it's going to be 0.45 divided by 0.01 over the total, which is 35. Okay, so the last question is asking you, from what supplier was the microchip most likely purchased? We will check the highest probability. The highest one is coming from supplier B, so we can say that the microchip was most likely coming from supplier B. Okay, so that's all for the probabilities. I hope that was clear. Thank you for your attention.